I feel like when I started this podcast, you were on my dream guest list. What's driven so much of the improvements on the kind of lowering costs and improving latency side?
Part of it is, I think, better architecture. It's kind of crazy how good the models are at acting like human. We've just been seeing an explosion of techniques there.
Are we going to see competitors to different parts of the NVIDIA ecosystem?
I think certainly there's lots of competitors are trying to enter the space.
What's that question that's outstanding that you're most curious to know or would most impact the direction of your work?
The question I'm trying to answer for the next couple of years is...
TreeDAO has driven many of the most important breakthroughs in AI over the past years. He was a lead author of Flash Attention, which has been a key reason why model inference costs have gone down so much. He was super involved in safe-based model work via his work at Mamba, the alternative architectures to transformers. He's the chief scientist at Together, and his work's been so impactful that SemiAnalysis basically noted that a huge part of the NVIDIA moat is the fact that Tree's doing all this work in the NVIDIA ecosystem. It's a real privilege of unsupervised learning to get to sit down with someone like Tree and just ask him anything that's top of mind, including the percent of workloads that are going to run on NVIDIA chips in 2-3 years. We talked about the future of AI hardware and where the opportunities are. We talked about how AI coding products have made Tree 50% more efficient in his work, which was way higher than I'd expected. And we also talked about, his thoughts on the future of alternative architectures to transformers and what might really work. Just a fascinating opportunity to talk with someone who's so brilliant in his field. Really, really enjoyed this conversation, and I think folks will too. Without further ado, here's Tree. Well, Tree, thanks so much for coming on the podcast. Really appreciate it.
Yeah, sure, for sure. I'm really excited about this.
I feel like when I started this podcast, 2.5-3 years ago, you were on my dream guest list. And so I think that was when kind of Flash Attention, was initially making the rounds and people were just oohing and ahhing over the impact you were having on the space. And I was like, if we really can build this up over time, maybe we'll convince Tree to come on. And so
yeah. I'm very honored to be here. I mean, this should be really fun. Yeah.
So I think we'll hit on a bunch of different things, that I think will be of interest to our listeners. I figured one place to start would just be a classic VC question, so you'll have to forgive me. The NVIDIA story over the past years has just been, unbelievably impressive to get to the scale they're at. And obviously you've contributed a tremendous amount to that ecosystem and making, that hardware, better and better for folks to use. Are we going to see competitors to different parts of the NVIDIA ecosystem on the chip side, on the kind of systems that package GPUs? Obviously, you've got, Google and Amazon with their own chips, but, for the vast majority of the rest of the industry, I'm sure this is something you think about a lot.
Yeah, I spend a fair amount of time thinking about the chips. I think certainly there's lots of competitors are trying to enter this space. I mean, AMD has been here for a while. Obviously, Nvidia is dominant for a couple of reasons. They design very good chips, and they build very good software, and that creates this ecosystem where people build on that. People build software on top of that. But I think certainly we'll see a lot of competitors entering the space as the workload starts to be a little bit more sort of coalescing around on the architecture side, transformer and MOE and so on. It becomes a little bit easier to design the chips for that kind of workload, right? So if you just focus on inference, I think AMD has certain advantages. They have larger memory and so on. So we're starting to see folks picking that up. On the training side, it's a little bit more difficult. I mean, networking is one of the main bottleneck, and NVIDIA is certainly ahead there. But I think people understand what are the challenges to build good training chips, what are the challenges to build good inference chip. So it comes down to execution. So I would say this space is actually really, really exciting. I talked to lots of folks who are designing new chips, either inference or training. So I would expect in the next couple of years, maybe some of the workload will become multi-silicon. They'll probably run on different chips rather than right now. I'd say 90% on NVIDIA.
Do you think the architectures are stable enough? Because obviously, I think one of the fascinating parts of chip design is you're basically making a bet 2-3 years in the future of what inference workloads and training workloads will look like.
Right.
And so obviously, the more certainty you have around that, the easier it is to make optimizations.
Yeah.
Does it feel like there's enough stability to make those bets, or is the idea that basically, look, there's dozens of startups that are and companies that are making bets, and one or two of them may work out?
Right. Yeah. So I think on the architecture side, from a very high level, it looks like it is sort of stabilized around transformer. But once you look a little bit closer, there's actually quite a bit of change around that. So the most recent one in the last couple of years has been mixture of experts. So where you make the model much larger, much more number of parameters, but sparser.
Yeah.
And so that has certain trade-offs. You need more memory, but maybe the amount of compute you do is a little bit smaller. And so even that prevents difficulty for some of the chip maker, because maybe they were designing for a dense model where it's very uniform compute, and now you have something sparse, so it's a little bit harder to design for. Or some of the stuff changing around. Attention has been around since for 10 plus years. But there are changes here and there that actually make some of this stuff difficult. So DeepSeek has this thing, multi-head latent attention, that looks a little bit different than attention. For example, they have very large head dimension, and if your systalker, right, the matrix multiplication engine has a certain size, maybe it doesn't fit, right? Like weird things like that once you look underneath the cover. So I would say that's one on the architecture. And then on the workload side, I think people are using these models for very different kinds of workload, right? Do we have the traditional chatbot? Traditional as in the last 2-3 years.
I feel like it's been around 3 years. It's traditional in AI world,
right? But there are new workloads like this kind of coding workload, like Cursor and Windsurf and so on. There's a kind of agent workload where it's not so much just like running the model, but also making tool calls. Running Python interpreter, doing web search, and so on. That presents challenges of how you design the chip. If the chip is very much focused on like just running the model as fast as possible, you might neglect things like how you going to connect to the host to run a web search, that kind of thing. I would say even though from a high level, the architecture has kind of stabilized, but underneath the cover, there's still a lot going on. And part of it is the workload is also changing. So it's a constant race of how fast can you execute and adapt to these new workloads.
So if 90% of these workloads are on NVIDIA chips today, where do you think we are in kind of 2-3 years?
Yeah, I think on the inference side, some of it will diversify, and we're starting to see companies like Cerebras and Grok and Semanova really presenting a serious challenge. Like they were pitching, hey, we can get very, very low latency inference, right? And that's fantastic for some of the use cases. So we talk to customers who really, really care about as fast, as low latency as possible, and they're willing to pay more for that, right? So I think we're starting to see more of these niche areas where people really care about low latency, or some people really care about very, very large batch, high throughput inference. Those things like just massive data processing or synthetic data generation, or RL training, where you have to just roll out and generate as many trajectories as possible. Yeah. So I would say it's going to diversify simply because the workload are going to diversify. Like
totally.
Whether low latency or high throughput or something else, maybe video generation that will require sort of a different profile in terms of how much compute do you need and how much memory do you need.
If you were like a startup today, it kind of feels clear in the moment, hey, here's all the different optimizations one might want to make given all these use cases. And then you kind of decide, hey, we're going to make a chip that optimizes for these things. And you wait for tape out and the actual ability to produce. And by the time you've done that, it's a few years down the line.
Yes.
And do you think that it's clear enough like what the different optimizations are going to be such that you can kind of make that forward-looking bet? Or is there such a risk that actually 2-3 years from now, if we're doing this episode, you're like, well, actually the optimizations that matter are like these 5 things that we didn't talk about?
Right. So I would say if you're a startup, you have to make a bet, right? You invest, so you know this, and you have to make an outsized bet. So you could bet that, hey, maybe chatbots will go away, and the thing that people really, really care about is, I don't know, video model, video generation model, or world model, or robotics, or something, right? And you make that bet, and you say, okay, that's probably going to be, 50% of the workload. How would we design for that workload, right? And you hope that your bet will be correct. I mean, that's the role of startup, right? Yeah. And I think that's probably the way you could make an impact. I think if you just if you don't place a bet and you say, I'm going to optimize for just the general workload, then the incumbents are going to just out-execute you.
I was excited we're doing this episode today because yesterday I was just scrolling Twitter as I'm wont to do, and I thought there was this really interesting tweet from Semi-Analysis and reaction to some of your recent work. So obviously you've done so much on optimizing models on NVIDIA chips. And I feel like, one could try and quantify the value you've added to the broader NVIDIA ecosystem, but it's clearly like massive. And I think the Semi-Analysis folks were like, God, like you've added so much value to this ecosystem. Well, why wouldn't AMD or Google or some of the other folks that have chips like try to pay you to get you to do similar optimizations in those space. And it kind of, obviously, it reminded me of the LLM world where, you've seen kind of massive packages for, the few researchers that are really able to to build and train these models. I wonder what your reaction was to that tweet and generally what you think about like similar dynamics in the hardware space.
Yeah. I personally work with lots of folks from Nvidia, AMD, Google, and Amazon, and so on. I spend a lot of my time on Nvidia chips simply because this is what we have right now. That's what most people use. I think they design very good chips and they design very good software for that. So that allows me to sort of do interesting things. That's kind of what I'm after. Like, can you do interesting things? We've worked with the folks at AMD on, for example, they had a version of Flash Attention, and we work with them to sort of integrate that in the public repo and so on. So certainly we work with some of them. I don't know what the best arrangement would be. But nowadays, I'm thinking a lot more about like what are the abstractions we need, not just for NVIDIA chips, but for sort of GPUs and accelerators in general. I spend a bunch of time at a lowest level trying to figure out get the maximum performance out of these chips. But as we scale at Together, we think about how do we get other people that we hire to get productive. Right, and part of it is building abstractions that will work on NVIDIA chips and potentially other chips as well. The other thing I'm excited about is what kind of abstractions do we build so that AI can do some of this work for us, and I think the answer isn't quite clear yet, but I think as humans or as technical leaders, like it's about building the right abstraction so that other people can get onboarded really, really quickly, so that the kind of things you do could work across different kind of chips or different kind of workload. Do
you think we're at a place where there are abstractions that do allow you to do work across the different set of chips out there?
I think we have some, right? But there's a usual trade-off, right? Triton is really, really good, and it supports NVIDIA chips, supports AMD GPU and Intel GPU and so on, and that requires them to design sort of a front end, and then there's a back end, and sort of different companies will contribute code to the back end. I think Triton is actually quite good, and a lot of companies are betting on that. Meta, for example, PyTorch, Torch Compile will just generate Triton code and then rely on Triton to generate code for NVIDIA or AMD. But that's the usual trade-off, which is, hey, if you don't control at the lowest level, maybe you give up some performance. And it's about like where that trade-off point is. If you give up 5% performance and you become 3x more productive, like for sure, that's an acceptable trade-off. But if you give up too much performance, then maybe people would go with something that's a little bit more lower
especially
level.
a pretty competitive inference market.
Right. So I'd say designing for humans is really, really hard. I think I would say hardware portability is kind of a myth. Simply, even for our NVIDIA chips, like generation to generation, they change a lot. And I think that's kind of the only way we get more performance out of these chips. It's not like a CPU where, year to year, maybe you get a 5 to 10% faster, and your old code just kind of works. Even for NVIDIA, every generation, they essentially have to rewrite all of the code. Because the way to get more flops is you build more specialized components, maybe lower precision, maybe a different way to synchronize between different parts of the chips, right? So there's NVIDIA also essentially rewrite their software every 2 years or so. So even hardware portability, even between generations, isn't quite there.
So those abstractions would be valuable even just to help you with each subsequent generation of chips from the same manufacturer.
Right. Yeah. So I think Triton has very compelling abstractions. And they even have something that's a little bit lower level, things like, I think this is super new, it's Gluon, where it exposes more of the hardware at the cost of maybe being less general, right? The folks at Modular has been building this language called Mojo.
Where what do you think of what they're doing?
I think it's super cool. Like, I think they have some of the right abstractions. It's just about execution, I would say. because people are going to look at it and they're going to be like, okay, how fast are you on Nvidia chips? Which is a really sort of, in some sense, unfair question, but that's what people care about. So they would design the abstractions, and then they have to do like some custom work to make it their code run really, really well on Nvidia chips, and then they do a little bit of custom work on for AMD chips, right? So it's just like, how much do you want to do the customization? So for just trading off performance.
It seems like the market demands the best inference on NVIDIA chips.
And we're seeing more and more of these sort of libraries or domain-specific language. The folks at Stanford have this thing, Thunder Kittens, sort of trying to abstract some of this. This Thailang. Google has this thing, Mosaic GPU. I'm sure I'm forgetting some, right? But I think people realize that there's a problem of like, we don't have the right abstractions yet. It's actually kind of painful to train new engineers to write very performant GPU kernels. So the answer is to build abstractions. And I think we're very much in the phase where we're iterating pretty quickly. That's why we see so many of these domain-specific language coming out, right? And then as the sort of the AI model is getting better, one of the things I'm thinking about is like, how do we design domain-specific language or abstractions for language models? Because they operate somewhat differently from humans, and we don't know what the right answer is. So I would say in the next 1 or 2 years, I think it's going to become a lot clearer. Right now, it's just everybody's is trying lots of different directions.
Where do you think those abstractions are most likely to come from?
Yeah, I think this abstraction, I would say people approach it from two angles. One is from sort of the machine learning side. They think about, okay, what kind of workload do we have, and what are the primitives that are necessary to express those workloads? So, a lot of workloads, let's say inference is very much how can I move memory as fast as possible? Inference is usually memory bound, right? Or how do I do matrix multiply as fast as possible? And what are the primitives I want to express there? The other angle is people thinking sort of from the hardware side. They have really cool sort of specialized components on the chips, and they're thinking about abstractions of how to expose these abstractions. So one of the things NVIDIA has been really good at is this sort of designing chips that are more asynchronous. Because the matrix multiplication is getting so fast, it's ridiculous, that everything else becomes much slower. So it's much more important to sort of overlap the computation of matrix multiplication and everything else. So how do you design abstractions that allow this kind of asynchronous execution? Things like they have the things, pipelines and synchronizations and so on. So I'd say that's where the abstractions are going to come from, either from the workload side or from the hardware side. I think it will become a lot clearer in maybe 1 or 2 years.
Well, you've alluded to it a few times, so I have to ask you. You talked about kind of making these abstractions, suitable for LLMs, maybe, as well as kind of just using AI in these processes themselves. How much are you using AI itself in determining this stuff, and how do you kind of see that changing over the next few years?
I think models are starting to become useful for this stuff. Actually, very, very recently, this really surprised me. On one level, what people are after is like fully automatic GPU kernel writing, right? You describe the problem, and the LM will just generate the kernel for you. This is kind of maybe we're there with some of the other areas like simple Python script or data analysis or web front end, right? Yeah, you can do this, right? So could we do that for GPU kernel?
Just vibe code some kernels.
Right. I would say if that's what you want, then I think we're very, very early. So these models can generate some simple kernels, like element-wise. You take in an array and you do some operation on each element, right? Or you do some kind of reduction, like summing and some normalization, things like that. So the models can do a reasonably good job. But once it gets a little bit more complicated, these models just don't generate correct code. I think it's just a function of we don't have enough training data. Training data is really, really tough for this stuff because if you scrape the internet on for kernel code, you'll get, I don't know, class projects. You'll get documentations that were meant for GPUs maybe 3 generations ago that, these are the things you shouldn't be doing now, kind of thing. So training data is really, really difficult. So I think the answer to that is you probably have to start with some expert level data, and then you generate synthetic data out of that, or hooking up to a tool like compiler and profiler, so that you can get lots of training data, or getting the right environment, right? I think it will be solved in a year or 2, but it's certainly a difficult problem.
Who has that data?
I don't think, this kind of data, I don't think is private. There are a couple of places where you have expert level code, but I think it's more about sort of the workflow. How do you start from a small amount of expert level data and generate lots of synthetic data, right? So I think the folks at this Discord GPU mode, they've been really trying to do this. So they took compiler, the PyTorch compiler, which go from PyTorch code to Triton code, which is this lower level kernel code. And they could generate, I don't know, I think 15,000 pairs of these program of PyTorch and Triton, right? Like, you have to be a little bit creative. I think there's just not that much data on the internet, so you have to be a little bit creative of how you're going to generate this kind of data. So I'd say that's one angle. If you want fully automatic kernel generation, I'd say we're super early there. The other side is, can it work alongside humans? Can models work alongside humans? And I've been pleasantly surprised that these models are actually quite useful.
Was there a specific moment where you're like, whoa, these models have gotten good enough to be quite helpful to me?
Yeah. I would say maybe there were 2 recent milestones. One was O3. O3's gotten really good at reasoning. Some of the questions I was brainstorming with O3 and GPT-5 was like, hey, I have this function, like, how would I optimize it? What are the things I would pay attention to? And it's like surprisingly good at the high level. The other one is Claude Code. Somehow it's actually pretty decent at writing Triton kernels, which is fantastic. Like, as much as I love writing kernels, like, a lot of my time is thinking about the design, thinking about, what kind of architecture should we design so that we can take advantage of the hardware. And so the implementation part of it is, design is really fun, but the implementation is usually quite heavy. Right. And Claude Code turned out to be quite helpful here. Like, I would say, it makes me maybe 1.5x more productive.
Wow. I mean, that's pretty good.
Yeah. So I've been a heavy user of Claude Code. If you have these models working alongside with humans, maybe they are a lot more helpful rather than just relying on them fully automatically generating kernels. Right?
What are the next milestones you're waiting for? I guess when a new model comes out, are there things you test that you're like, God, if the models could just get to this stage, I'd go from 1.5 to 2x.
Right. So I would say I think Claude Code is a good example of a kind of a step change where it's a lot more agentic, right? And somehow, they post-trained Claude to do really well there. And I'm sure, other folks, OpenAI and Google will soon get to a very, very similar point. So agentic here just means it can use tools really, really well, and it knows when to use the tools. So it knows that, hey, I'm probably not having the right API, so how do I look up the API? Or, the program is not compiling, or the program's not fast, how do I get information from the profiler? That sort of thing, right? So I think I would say for new models, I would see how well they know whether they don't know. Right. When do they need to seek out new information? And that's kind of a vague thing. I think people are starting to come out with benchmarks for this kind of agentic capabilities, but we're still super early there.
You've been such a seminal part of so many of the improvements in the AI inference market since the launch of ChatGPT and the broader usage of a lot of these models. So I figured maybe just for our listeners, it would be great to contextualize these last 3 years and kind of what's driven so much of the improvements on the kind of lowering costs and improving latency side. And I want to make sure to give you an opportunity to talk about a lot of the Flash Attention work as well. For
sure. Yeah, I think in the last couple of years, inference cost has probably come down maybe 100x.
Yeah, at least.
Right? Since ChatGPT debut. I think, it's probably reflected in the API cost as well. So on one side, is on the modeling, people have just trained much better models for the same sort of number of parameters, right? And part of it is much more data. Part of it is, I think, better architecture, right? MOE certainly helps. People invent new sorts of efficient attention and so on, right? So that's on the modeling side. The model's getting much better for the same number of parameters. The other side is on the inference optimization, and we've just been seeing like an explosion of techniques there, right? I think in the early days we didn't, as a whole, we didn't understand what are the bottlenecks of inference. And after a while, people realize, hey, it's a lot about data movement, moving the weights in and out of the memory, moving the KV cache, which is the part of the attention operation that you need to store the history, entire history to sort of make the next prediction, right? So a lot of optimizations are around how do we reduce the data movement. So things like you could quantize the model, right? So you use, instead of typically, I think maybe 2-3 years ago, it was typical to use like 16 bits per parameter. Yeah. But now people are doing 8 bits is pretty common now, and some new models are using 4 bits. There's some work using like 1 or 2 bits, which is pretty crazy. But you see this really this compelling trade-off. As you quantize the model, a lot of times you pretty much don't lose any quality, and that requires fairly sophisticated techniques, but that has worked amazingly well, right? Yeah. So I think the most recent sort of OpenAI release, GPT OSS, they released most of them. Most of the layers are in 4 bits, right? Which is crazy. They have, I think total was 120 billion parameters, but because each is using 4 bits, you could fit that in like 60 gigabytes or something, right? And that has translated to really good inference performance. So quantization is one. The other one is like this co-design of model architecture and the hardware. As people understand much better, as essentially like people on both sides are talking to each other a lot more, right? I think Flash Attention was kind of like that, where there were people who understand the hardware really well. There were people who understand the algorithm and the model really well. But as you combine these ideas, you start to see, I see exactly what the bottleneck on the hardware side is. So how do I change the algorithm? Yeah. And for Flash Attention, it was like we realized memory access was the main bottleneck, and we figured out sort of a new way to rewrite the attention algorithm to reduce memory access, right? And we're seeing that a lot for inference. So an example is this variant of attention from DeepSeek called multi-head latent attention, right? Where they realized, hey, a lot of time is being spent on compressing, moving the KV cache, which is a summary of the history, right? And they realized, hey, we could make the KV cache much smaller by they call it this latent projection, where you project on a much smaller space, right? And that turns out to work really well. And DeepSeek, I think in the paper, they said they were able to serve this model very efficiently. Right? Yeah. So that's one example. The other one is a mixture of experts, where you don't, for each query, for each token, you don't use all of the parameters in the model. There's some sparsity, so you use some part of the model. And in the last couple of years, I think the trend has been making the models sparser and sparser. Yeah. Right. I think for the first open source MOE model from Mistral was maybe 2 years ago. They activate 2 experts out of 8 experts per layer, right? So it's a ratio of 25%. But now for DeepSeek and OpenAI model, you activate, I think for OpenAI GPT OSS, it was 4 out of 128 or something, right? It's a factor of 32. And we're getting sparser and sparser. So that's really good for if you serve lots and lots of users, right? Yeah. So people are really understanding the workload. They're really co-designing the architecture with the inference, and I would say that's where a lot of improvement has come from. Is this co-design between model and the inference stack.
And then looking forward, like where do you think it's going to continue to come from?
Right. So I think there's got to be another 10x or so.
All right.
Right. I mean, if you just
seems to be the trend so far.
Right. Extrapolating.
I just didn't know if we'd picked off the low-hanging fruit, right, or if they're still
right. I think it's we've done as a whole we've picked up a lot of low-hanging fruits for sure, but I think there's still lots to do. One is actually on the hardware side, which is for a while because you couldn't really predict what the workload is going to be 2 years from now.
Yeah.
So you couldn't specialize very well, but as the architecture has gotten a little bit more stable, I think people designing chips are optimizing for inference now, right? So low precision, get really good native hardware support. All the networking gets really good because as the model gets larger, things like mixture of experts, the models get larger, but you don't activate all of the parameters. You might need multiple GPUs or chips to store the model, and then networking becomes much more important.
Right.
So I think on the hardware side, it would probably be 2-3x just in 1 year. And on the software side, I think a couple of things. One is pushing on the model architecture. So I've worked on things like Mamba, and it's a way to sort of, instead of storing the entire history as a KV cache, you could have the model compress that history into a smaller state vector. Right? Of course, that's going to have certain trade-offs and so on, but we've seen pretty good success with this. And I think this is going to be especially important for large batch inference, which is what people are, some of the workloads are demanding these days, where things like test time compute and reasoning, like what you really, really want is you want the model to explore lots of trajectories or chains of thought at the same time, right? I think Google came up with this thing, Gemini DeepThink, I think, which is that was the idea. I mean, they were winning IMO gold medals and so on, which is they explore multiple paths at the same time. And what that means is that you're doing model inference on like hundreds of sequences at the same time. And there, the KV cache become a much, much bigger problem. So you could try and get the model to sort of compress that KV cache. That was sort of the direction we were going with Mamba, and there's been a bunch of other variants coming out along that idea. So I think on the model side, it's going to be 2-3x.
Yeah.
Right. And then on the just like kernel level, lots of people are getting really interested in the kernel side, and some of them are very, very talented. So we're getting very, very good kernels. And that's probably another 2x or so. So taken together, I think even in just 1 year, we would probably get another 10x.
One thing I'm struck by is obviously with this broader like diversifying of use cases and how people are what they want to run inference on and the architecture of these models, it seems like it's kind of expanded into, there's many different end use cases, and the bottleneck of each of those or the optimizations you want to make each of those are different depending on.
Exactly.
And so I guess what are the implications of that then, maybe to bring back to Together as like an inference provider? Obviously you want to be the best at all of those things. Yeah. Do you think that like the ecosystem, remains with one vendor who is, really good at all those things, or do you see like specialization over time where it's like, okay, cool, if you're trying to run a deep research, like there's one inference provider that's amazing at that, and if you're trying to run like more of a chatbot use case, how do you see that kind of playing out?
Right. Yeah. I think there will probably be maybe 3 kinds of workload patterns. And I think all inference providers will understand this and they will optimize for it. But there's certain advantages to running at scale, right? Yeah. So on the workload side, there's the traditional chatbot where you need a mix of interactivity. So you can't be too slow, but you also don't need to be super fast.
Yeah. Sometimes it's like a little creepy if it comes like right away. You want to like feel like for the experience that there's someone at least doing a little bit of thinking on the other end.
Right. So there's that kind of workload. There's the kind of like really low latency requirements. So things like I spend a lot of time with Claude Code. So I always wish, hey, if this is like 3x faster or 5x faster, I'm certainly willing to pay more. Yeah. Right. And so we'll see more of that, where this kind of like very interactive, where if the model is 2-3x, or if the inference is 2-3x faster, the person working with the model is going to be 2x more.
Yeah, it's the difference between like staying in flow state and not.
Right. I mean, people are getting around this problem by running multiple of these models. So, having like 4 Claude codes running at the same time, that kind of thing. But for someone who, I personally prefer deep work, and when I work with the model, I usually just use one, which my partner yells at me for. She's like, you should be using 4 Claude codes at the same time. But for this kind of workload, people probably will be willing to pay more for this low latency. So that's the low latency sort of agentic kind of workload. And then there is the very large batch. I don't care so much about latency, but I just want as high throughput as possible. So this is important for things like generating synthetic data. So as I mentioned, a lot of the way people the way people are training models now is that they have a small amount of expert level data or the human annotation data. Right. I don't know. Let's say you're in airlines and you're trying to get build an AI agent to like resolve customer complaints or conflicts and so on. They have a small amount of really, really good data, and then you can generate tons of synthetic data out of that. It's kind of crazy how good the models are at acting like humans. You can say, hey, if can you act as if you're this kind of this customer from New York who is annoyed at that their flight is delayed out of LaGuardia. I don't know. All right, and models are surprisingly good at acting as humans.
Yeah, I'm scared that we've taught them the capabilities to be angry New Yorkers at an airport. That's not like humanity at its finest. So
yeah. But somehow there's lots of that data on the internet where the model has learned that, right, and the model can then use that. I mean, they have this kind of world model internally that they can then generate lots of data that, probably not as good as human data, but you can generate a massive amount, right? And for that kind of use case, inference use case, you really only care about throughput, right? The other one is for this RL training kind of use case, where on one hand, you're training an agent to do something, change its policy. But the way part of the training loop is that as the model has some policy, you need to evaluate how good that policy is, right? So let's say I'm training an AI engineer. How would I know how good the current AI engineer is? And that requires me to sort of sample from the model, and it's called rollout. So you sample tons of completions from the model, and then evaluate how good that is, right? And so as part of this training, you really need very, very large batch, high throughput inference. So I would say that's the third use case, very large batch. And so for these 3 use cases, I think people are starting to recognize these patterns, and as instrument providers, we certainly do sort of different optimizations.
How do you think about allocating your resources across the 3? Because obviously, I'm sure there's different optimizations that are focused.
Right. So I would say this is where maybe running at scale really helps. So we call it fleet level optimization, where if you're running on inference on thousands of GPUs, you can sort of dynamically change the cluster allocation. So as an example, this very easy simple example is running batch inference, batch API. OpenAI has an option for that. We also have an option for that where if we see that the cluster is not so busy with these more interactive queries, we can just send in these batch queries that can sort of soak up the compute, right? And as a result, we can provide, I think we give like 50% discount on batch API, and I think OpenAI does the same, right? DeepSeek probably does that too.
Having it at scale really helps.
Right.
As you think about kind of like the evolution of the inference market, does it feel like there's endless optimizations to do over time, and so it's always possible to stay a little bit ahead of the rest of the players, or at some point have the low-hanging fruit been plucked on each of these, and it's actually about building a broader platform to do other things on top of these workloads?
Early on, there were lots of low-hanging fruits, and if you write reasonable kernels, if you build a reasonable inference engine, you get much better results than what was out there. But now I think the open source tooling is getting very, very good, right? Things like VLM and SGLang, and some of these projects are very, very popular, and they've gotten to like production level quality, right? And we certainly, work with these folks and contribute and so on. So I think just the baseline has gotten so much better, right? But there's also just like newer and newer use cases. So customers come to us and they say, oh, we really care about prefix caching, or we really care about low latency because in our application we need this requirement, all right? Or they're like, hey, we're actually not doing text, we're doing video, and that's sort of a different trade-off, much more throughput oriented, and we work with some of those customers. So even as the open source tooling, the libraries are getting so much better, I think the workloads are evolving so fast that there's always sort of new stuff to do, right? And there's this kind of explosion of like the models are getting so good now that there's so many ways to extract value out of these models. That's why we see so many startups building on these models. And as a result, the workload is going to evolve pretty rapidly.
So you think, obviously we have these like three kind of main categories of workloads today. Do you feel like fast forwarding a year or two from now, it's like 27 or like, a ton of different ways and each requiring its own kind of optimizations?
I think it's still going to coalesce, right? I think the kind of agentic workload might be a killer use case.
Yeah.
I think it's maybe a step change from maybe ChatGPT was a step change in terms of application, right? That was sort of the first time users are exposed to this kind of language models. They can talk to and maybe solve their help them debug their code or look up informations and analyze information and synthesize information. But I think the next set of application is going to be agentic, which is, hey, can these models sort of take actions and collect information by themselves, right? And that is going to require sort of a different sets of optimizations, right? So now it's not just running the models really, really fast on GPUs. It's like, how do you connect with the tools that humans usually do?
Yeah.
Web search is an easy example. But as these workloads move to different verticals, let's say you're an engineer, I don't know, you're designing airplanes or something, right? You want the model to be able to access your design software, right? Or if you're a financial analyst, you have certain database that you want the model to tap into, right? So I think this kind of workload will be one of the main workloads that we have in the next year or so. That's my prediction.
No, and that systems level work around agents then obviously becomes a whole new set of problems to solve.
Right,
and so it feels like even if the original set of workloads, there's great open source tooling, there's now entirely new set of workloads that also require optimizations and getting into some of that systems work and accessing like external databases and other things is different than just optimizing inference, but it seems like a natural evolution of the product you guys are providing.
I think that's going to be the main use case for more like professional level or enterprise level. I think on the consumer level, I think one of my bets is like we'll get real-time video generation. And we're starting to see some of that, and I think it's going to really change sort of the consumer landscape to the effect of like TikTok really changed that landscape, right? For better or for worse, I don't know, but it's very, very engaging, right? And so on the consumer side, I think it's some of the companies we work with, like Pika Labs and Hydra, they're focusing on real-time video generation. That's the bet, right?
There's a whole new set of problems to solve.
right. And so it's just a lot more compute. Like video generation is very, very demanding on the compute side. So that might be fueling even more chips, even more inference optimization.
Super interesting. I mean, obviously you're conducting a lot of research and making these bets ahead of, there's all these big outstanding questions of where the space is headed. I'm curious if you could, fast forward to the future 3 years from now and get the answer to like one question in the AI infrastructure world that would really help you shape your direction today. Like, what's that question that's outstanding that you're most curious to know or would most impact the direction of your work?
The question I'm trying to answer for the next couple of years is, how do we get AI to expert level? Right now, I think the models are at the sort of the median human level on some of the tasks. Like front end programming, they've gotten quite good.
Yeah.
Actually, the models are much better than me at front end programming for sure. Or analyzing data. That kind of task where there's lots of data on the internet. Whenever there's lots of data on the internet, these models are gonna just crush it, right? So they've gotten to sort of the median or maybe slightly above average level on some of these tasks. But I think the economically valuable tasks are still there, right? We pay lots of money for human experts in, designing airplanes or designing hardware or, doctors and lawyers and so on, right? Those people become expert because they spend time, working with specialized tools. They spend time.
They don't have an internet worth of data that is why they're experts.
Right. So how can we get models to get to that level, to work alongside with humans at that level? I think that's where a lot of the economic value is going to come from. Right?
And obviously then the hardware optimizations you have to do around whatever the way to do that is. You've worked on state space models. You've spent a lot of time thinking about alternative architectures to transformers. I think your collaborator Albert Gu said that transformers are not going to be the final solution by themselves. Like, do you think we need architectural innovation to get us to that level?
Right. I love Albert. Right. But maybe this is where we disagree a little bit. Right. So I think to get to AGI or ASI, it's possible that the current architecture we have is sufficient, right? But at what cost? Which is, hey, if you have a better architecture, maybe you get there, 1 or 2 years sooner.
Yeah.
Like that's probably worth it. Or you get there with 10x less of the cost, right?
Which ultimately flows to then the accessibility of that ASI when you get there.
Right. And that's certainly crucial because we're spending $500 billion on AI infrastructure every year. Don't quote me on that, but I think like that's the sort of the right ballpark.
Yeah.
Right. So do we need to spend 10x that, which seems somewhat unrealistic, or with better architecture can we get there with the current amount of spending or maybe even less? So I think that's where the model architecture is going to play a role, which is can we get to AGI with a better architecture? I think the current architecture sort of have all the right ingredients. And if you keep scaling, which people have been doing, you could get there, but maybe, the cost is just a little, is like astronomical.
What other architectures are you paying attention to?
Right. So I'm pretty excited about a mixture of experts, especially getting sparser and sparser. We're trying to push that limit, like how sparse can you go? And we're working on that. I think it's been a compelling direction. Some really important work done by DeepSeek showing that you can make these things really, really sparse. There were even earlier work from DeepMind pushing in that direction as well. So I think that's one compelling way to sort of get more intelligence out for the same compute. Ultimately, I think we want to optimize inference per dollar.
Yeah.
Right. And that means it could be factored into inference per flop, which is floating point operation, and flops per dollar, which is inference per flop is more like architecture, design, data, algorithms. And then the other side, flops per dollar, is like hardware and kernel optimization. So on the architecture side, we're trying to extract as much information, as much intelligence out of the same computation.
Yeah.
So mixture of expert is one. I think some of the state space stuff done with Albert has been really, really fun, and people are picking that up. Right, we've collaborated with a bunch of folks from Nvidia, actually training models. They release several of these where they show, hey, they can get really, really high quality model using this kind of architecture. It's a hybrid of transformer and Mamba and so on, but with much smaller cost or much higher inference performance. Right. So I think architecture is very important for this, for inference. I think that's the utility of architecture research. And nowadays I think about very much, I call it like inference first architecture design, which is, most of the flops are being spent on inference anyway. So you really, really want to design architecture that make inference really, really good.
Well, I'm struck by, obviously you push forward the inference side with Flash Attention, with Mamba, you've been a pioneer in state space models. I'm sure folks are curious, like, What research areas are interesting to you now? Like, where are you spending your time? What's the next big paper we should expect from you?
Right. I'm still certainly working in these areas. I'm still very much interested in these areas. But I'm exploring some new directions. Some of which involve working with sort of what are the next set of really impactful applications. I think robotics is one of them, right? And robotics. Like how far are we away from having really good, humanoid robots that work in homes? Maybe 5 years, maybe 10 years.
Yeah,
I don't know, right? And that usually means a lot of interesting and exciting questions on the research side that we want to answer. So that's a direction, on the research side.
Yeah. What's most interesting to you within the robotics research area?
So robots, we can initialize a model controlling a robot with some of the foundation models that we have already.
Right.
You can use a language model to do the planning. Like you say, if you ask a robot to pick up a coffee cup, then the language model can say, go walk over to that table and pick up the coffee and so on. But what's missing, I think, is this kind of interacting and acting in the world, right? Because we just don't have data for that. We have data, language. We have language data on.
Right. You've obviously seen some folks trying to scale simulation data. Other folks are doing teleop, but clearly a data problem on the actual actuation side.
Right. So that's certainly one. The other one is I think robots kind of have to process information in a sort of multi-resolution, multi-time scale way. So some of which is, if you're controlling the joints, you have to act very, very, very rapidly.
Yeah.
But if you're planning a route for the robot, you can do it much, much slower.
So it's like different architectures you might want to use. I mean, I'm struck. It seems very analogous to some of the state-space model work you've done.
Right. So taking explicitly taking time scale into account. Do I want to do very lightweight computation to just control the joints, or do I want to do much heavier weight sort of reasoning to plan the optimal route for the robot? So I think it's going to be this sort of composite system initialized from language models, vision model, audio model, world model. But how do you stitch them together? I think that's the big question.
Right. With some fascinating hardware questions to be able to run the stuff locally and and fast enough.
Yeah.
I feel like you could kind of probably work anywhere you want. And I think one really interesting thing is you're obviously, chief scientist over Together, but you've also, gone the academic route as well. And you're assistant professor over at Princeton. How did you think about kind of staying within academia and then also like the set of problems that it makes sense, like, in this robotic space, like you obviously, you could go work at Physical Intelligence or partner with some of these robotics companies or do the work from an academic setting. How do you think about like what makes sense to work on, within academia versus industry?
Right. That's a great question. And, your answer is going to be personal, right? For every person, it's going to be different. So for me personally, I actually like being both in startup and being a professor. It sort of like presents sort of different modes of thinking and execution. On the startup side, it's very fun because we move fast, right? Like, if things we want to do, we could get it done in days or weeks or at most months. Like that's the level of the horizon that we plan for. Right. And it's very fun. Like you get a team of really, really good people. They can execute very, very fast and you accomplish great things. And I'm very, very proud of the work that the team has done at Together. So that's been very, very fun. On the academia side, it's a little bit longer time horizon, and the kind of problems we think about are maybe more speculative. Right. We don't solve the problem that would need solution in a month. Like we think about, if the world is moving in that direction in 2-3 years, what are the interesting questions to ask, and what are the challenges to solve in 1 or 2 years, right? And we think in that time scale. So working with students has been very fun and rewarding as well, because we get to think about these questions that are interesting, sort of just intrinsically interesting, right? Obviously, there are certain trade-off, like the amount of compute in academia is much smaller. The way you evaluate it is, are your ideas interesting rather than, does it work and run really fast and so on. That's a different set of evaluation, right? So I think in academia is you have some more freedom to think deeply about these longer horizon problems. And I happen to like both modes of operation. So that's why I'm still at Princeton as a professor. I'm still involved in the startup.
Yeah.
Right. And I think ultimately it's maybe a mix of kind of exploration and exploitation. Like if you think at a macro level, academia's role is more on exploration, right? The funding comes from usually the government. The government cares about, can you explore tons and tons of ideas to see maybe 5 or 10% of those ideas will work out. I mean, as an investor, as a VC, like you, that's kind of the mode you operate in as well, which is, hey, we're going to explore lots of ideas. Maybe 5 or 10% of these ideas will become incredibly important, right? One example is attention, right? Attention, even though it got famous with the Google paper, actually came out of the work at Mila. It's with Dimitri and Yoshua Benjo and other folks, right? It was kind of coming out of academia, right?
Yeah.
And if you think of all the other sort of components in the current architecture, the optimizer, the Atom optimizer, was Jimmy Barr at Toronto and other folks, right? Layer norm, also Jimmy, right? And essentially, lots of what we have now came out of academia, because the role of academia is to explore lots and lots of ideas.
Totally.
And some of them will work, right? And then the role of big companies and startup is they take some of these ideas, they do innovate on them, they execute really, really fast, but they understand sort of what the market needs, right? What the product they should build, and they have this, a much bigger sort of financial power to make some of these bigger ideas happen.
Right. But the interesting thing about this funding environment is I feel like it's almost distorting some of that, where there's plenty of venture funding available for folks to do kind of more research lab. Like if you pitched, hey, robotics, is going to need different architectures and different hardware, over the years, someone might say, okay, cool, you're not going to monetize for 10 years, but like that's a really interesting idea, and here's a bunch of venture money to go out.
Right. Yeah. It's kind of crazy the kind of funding that folks are getting, right? Like in Ilya SSI, he was like explicitly, we're not going to build any product. But yeah, people want to give him money because he's Ilya for sure, right? And some of the folks, like you said, in robotics, are doing that. So yeah, I think people are in AI. It seems like some of these risks are starting to pay off. So people, on the investing side, people are much more willing to put in money. Yeah,
totally. Well, this has been a fascinating conversation. We always like to enter interviews with a quick-fire round where we get your take on some questions. And so maybe to start, what's one thing you've changed your mind on in AI in the last year?
These models are surprisingly useful even for my daily work at the sort of the advanced and expert level. Like they're surprisingly good at the math and coding.
Yeah. 1.5x is way higher than I would have expected you to say. That's pretty impressive. Do you think open source models are going to be closer or further in quality from closed source models in a year?
I would say closer. I think the scaling now is more on the RL side, and that relies actually more on tooling than just raw compute. So I think open source is going to do really well there.
What development in kind of the broader AI space do you think people aren't paying enough attention to right now?
Definitely data. I think data is always a little bit under hype. I think lots has happened on the data side. Synthetic data using models to rephrase, that has huge impact that maybe people have paid less attention to.
Do you have a favorite application that you've seen built on Together?
Yeah, we worked with some of these video generation companies like Pika and Hydra, and they're generating like viral TikTok videos with the models they train on Together and doing inference on Together. So it's been amazing. Yeah,
and that feels like poised for a lot of development.
Right.
Well, amazing. This has been a fascinating conversation. I want to make sure to leave the last word to you. Where can folks go to learn more about you, either your work at Together, your academic work, anywhere you want to point folks? The mic is yours.
For sure. Yeah. So my work at Together, we put out blog posts on Together.ai. I'm also on Twitter, tree_DAO. And once in a while I write blog posts on my website, so treedao.me.
Amazing. Well, thanks so much, Tree. This was fascinating.
Yeah, this has been really fun. Thanks.
Yeah.